Okay, now we're going to discuss tree enumeration. So we're going to count the number of trees there are at n vertices. And according to Cayley, the number of trees is n to the n minus 2. So when n equals 2, this exponent is 0, and you're looking at 2 to the 0, which is also known as 1. Here's the only tree on 2 vertices. On the other hand, once n equals 3, we see there are 3 such trees. And here our vertex set is always going to be the integers 1 through n, because that sometimes helps both with the proofs and with drawing the pictures. And in a tree on 3 vertices, there has to be a unique vertex of degree 2. And so there's 3 ways to pick it. And then the other 2 vertices have to be leaves. Now when n equals 4, we got 4 squared, which is 16. And so there are 16 possible such trees, and I've tried to draw them all. There's 4 that have a unique vertex of degree 3, and then there are 12 possible paths. So there's going to be 2 different ways we're going to see the proof of this theorem, neither of which are the way Cayley originally proved it. So the first is to actually find a bijection between trees and a set of sequences. So you're looking at sequences of integers whose entries are integers 1 through n of length n minus 2 with repeats allowed. Note there has to be n to the n minus 2 such sequences. Why? Because each entry takes on n possible values, and there's n minus 2 entries, and these choices are made independently. And so this bijection is called the proof for sequence, and you construct it as follows. So we're supposing our vertex set are the integers 1 through n. We're going to set T0 to be our original tree. Or actually, this should be T1. We set T1 to be our original tree. We're going to let Li be the smallest leaf of the ith tree. Note here that the leaves are numbers, so we can talk about the smallest such leaf. We're going to let Si be the neighbor of that Li. And then we're going to remove that leaf to get the new tree Ti plus 1. And then we're going to keep doing this. We're going to let L2 be the smallest leaf of T2, S2 be the neighbor of L2, and then remove L2. And then the proof for sequence is the sequence of the neighbors of our leaves. So here we show how to construct the proof for sequence in action. Suppose this is our tree. Our leaves are 3, 6, 7, 5. 3 is the smallest label, so I circle it. Its neighbor is 1, so I write down the number 1. That's the first entry in my sequence. And now I remove the vertex 3. So now this is my new tree, and this is my sequence so far. My leaves are 6, 7, and 5. 5 is the smallest, so I circle it. Its neighbor is 2, so I write down 2 to the end of my sequence. And then I remove the vertex 5. And so now in my remaining tree, my leaves are 6 and 7. I circle the 6. Its neighbor is 1, so I tack 1 to the end of the sequence, and then I remove the 6. And now finally we're at a new situation where we've actually introduced a new leaf, the vertex 1. So now my leaves are 1 and 7. And so even though 7 was available earlier, the fact that 1 is the smallest means that's the one I have to pick. Its neighbor is 4, so I tack 4 to the end of the sequence, and I remove that vertex. And now my leaves are 4 and 7. And now 4 is the smallest, and its neighbor is 2, so I write that down. And I terminate the algorithm once I hit an edge, for reasons that have to do with the fact that once you have a tree with 2 vertices, there's a unique such tree. And so the point is, this is my sequence. We see that repeats are in fact allowed, but you will notice that the numbers 3, 5, 6, and 7 don't appear at all. And we see that the 1 appears twice, and the 2 also appears twice, and the 4 appears once. And if you notice, the vertex 1 originally had degree 3, and the vertex 2 also had degree 3, and the vertex 4 had degree 2. So each vertex appears in the list 1 less than its degree. We also see that there were 7 vertices, and the vertex labeled 7 stayed all the way through to the end, because 7 is larger than every other number, so 7 could never be the smallest label of a leaf. And so in particular, this last vertex, vertex n, is adjacent to the last vertex in our sequence. In particular, from our sequence, we can determine the last edge remaining. So here was the first observation we had made. Any given vertex appears in this sequence, one less than its degree many times. And so to prove that, suppose that this vertex was the ith leaf in our process. Then it's worth noting S sub I is its neighbor in T sub I, so S sub I is adjacent to J. So there's one possible edge. Now let's look at other neighbors of J. If U is adjacent to J, we see that U can't be in Ti. Why is that? Because U is not Si, and Li is a leaf of Ti, so it only has one neighbor. So that means all the other neighbors of J had to have been deleted by the time you reach this point, which means it was removed by the algorithm earlier, and so U has to be equal to Lk for some k less than I. In other words, U had to be removed as a leaf earlier in the process. But how did we construct this sequence? As soon as we decided to prune off the vertex U, we recorded its unique neighbor in the tree. Since U is adjacent to J, that unique neighbor has to be J. So in particular, we see that J has to appear in the list one time for every neighbor of J except the neighbor Si. So we see the J appears d of J minus 1 many times. Moreover, since we remove J from the next tree, we know that J can no longer appear in the sequence after that point. And so that proves the result if we've removed J at some point in the algorithm. If J is never a leaf of any of the trees, is not the smallest label leaf of any of the trees, then it ends up being in the last tree, which, as we've discussed, only has one edge. By the same argument, all of its neighbors had to have been deleted, and so J has to have appeared d of J minus 1 many times in P of T, with that one remaining edge that's not being counted being this last edge. And finally, as already noted, since n is always larger than any other number, we see that the vertex n never gets removed, and so in the last tree, n is one of the vertices, and Sn minus 2 is as well. So the point is we can tell a lot of the structure of the tree from the proofer sequence. In fact, I say more is true. You should be able to construct the tree from its proofer sequence. So in particular, if two trees have the same proofer sequence, then they're in fact the same tree. And conversely, given any sort of sequence we think might be a proofer sequence, we should be able to construct a tree that has that proofer sequence. So let's focus on this claim first. So first of all, as we had already discussed, the set of leaves of the tree are the labels that do not appear in the proofer sequence. Since these two trees have the same proofer sequence, the set of leaves of T is also could be found by removing the entries of the proofer sequence from T prime. But that's also, as we've seen, the set of leaves of T prime. So in particular, these two sets are the same. So both trees have the same set of leaves. Now, how does our algorithm work? We take the smallest labeled leaf in T, which means we're also taking the smallest labeled leaf in T prime. So since these two sets are the same, we're taking the same leaf in both cases. In particular, the smallest element in these two sets must be a leaf in both trees. Since the proofer sequences are the same, this also means that this leaf must be adjacent to S1 in both trees. So we found an edge in common in both trees. Then what else do we know? Well, how does our algorithm work? We remove the vertex L1 from both trees, and then we continue our algorithm. However, since these two sequences are the same, when you remove their first element, the rest of the sequence remains the same. And so in some sense, by induction or by repeating this argument, we can guarantee that the t minus L1 is equal to t prime minus L1. And so we have two trees. They agree when you delete the same vertex, and that vertex must be a leaf in both. And in both cases, that leaf edge is the same. So in other words, these two trees must be the same. This tells you that the function that takes a tree and sends it to its proof or sequence is a bijection between the set of trees and the set of integer sequences of length n minus 2 containing only entries between 1 and n. However, to say something is a bijection, we also need to actually show that the function is surjective. In other words, given a sequence, we need to show that it's a proof or sequence of at least one tree. And we're going to do this by basically following the same process we used to construct the proof or sequence. Instead, going forward, we're going to start by constructing forests. And then at the very end, it ends up being a tree. And so the forests are going to be on the entire vertex set. And so I'm going to define a set of potential leaves, L1, to be the integers 1 through n take away the entries of the sequence. In other words, the things that we know end up being the leaves of the final tree. And I'm originally going to define my edge set to be empty. And so then we're going to iterate the following process. We're going to take the minimum element in our list of potential leaves. And then we're going to take our forest and we're going to add an edge between this leaf and the next entry in our sequence, Si. And then we're going to update our set of potential leaves. No matter what, we're going to remove the vertex Li from it. But we do run into this case. If entry Si appears later in the sequence, that's all we do. Otherwise, if Si no longer appears in the rest of the sequence, we add Si as a new potential leaf. That's because, in some sense, once you've hit this point, you've already determined all of the neighbors of Si except one. So let's actually do the construction. Suppose this is my sequence. Since it has length 5, and the length of the sequence is n minus 2, I know I need 5 plus 2 vertices. So n is actually equal to 7. I look at the list of numbers and I see 5, 6, and 7 are missing. So there's my set of potential leaves. 5 is the smallest number here. So I remove it. That's my new leaf. I look at the first entry in the sequence. It's a 3. And so I connect vertex 5 to vertex 3. And then I remove the 3 from my sequence and I look at what's left. I see the 3 no longer appears in the rest of the sequence, so I add it to my set of potential leaves, and now I'm at the next step. So now my potential leaves are 3, 6, and 7. 3 is the smallest such number, so I remove it from the list. 1 is the first entry in my sequence, so I connect 3 to 1, and I remove 1 from the list. I see 1 appears again, so this is the end of my algorithm, and I move on to the next step. So between 6 and 7, 6 is the smaller number, and so I remove 6 from my list. 2 is the first entry in my sequence, so I connect 6 to 2, and I remove 2 from the sequence. Since 2 no longer appears in my sequence, I'm going to have to add it to the list. And so again, that's all I've done so far. I've removed the 2, I have to add it to the list, I've removed the 6, and I've added the edge from 6 to 2. All right, so now I'm looking at my list of potential leaves, and 2 is the smallest number. And so I draw an edge between 2 and the first entry of my sequence, which is a 1. And then the 1 no longer appears in the rest of my sequence, so I'm going to have to add it to my list. And so this is my next step. There's only 1 entry left in my sequence. Again, 1 is the smallest entry in my list, so I remove it, and I attach it to the only entry in my sequence. And then I remove it, and at this point, the only leaf edge left is, of course, the largest vertex, n. And as discussed before, we always put that edge between n and the last entry in my sequence, which in this case was a 4. And thus we see that we do in fact get a tree. The proof of that fact relies on actually showing at each step in the algorithm that what you end up with is a forest. And that ultimately boils down to this approach we've taken, that every time we add a new edge, we remove an element from the potential leaf set. And then you just have to go and check why that shows that you can't end up with a cycle. And so you end up with a forest that has the same number of edges as a tree, so it must be a tree. And so as mentioned before, there are n to the n minus 2 possible sequences of numbers 1 through n, s1 through sn minus 2, and thus we've proven Cayley's theorem. And now we get at a generalization of Cayley's theorem. The matrix tree theorem is going to be about the number of spanning trees of a given graph G. So given a graph G, we're going to define a new matrix where we've subtracted off the adjacency matrix from a diagonal matrix whose diagonal entries are the degrees of our vertices. Now, equivalently, you could define it this way. The ijth entry of this matrix is the degree of vertex I when you're on the diagonal. It's -1 when I and j are adjacent, and it's 0 otherwise. They refer to this as the Laplacian of the graph. So for instance, if I take this graph labeled with these vertices, then we see that the degree of vertex 1 is 3, the degree of vertex 3 is 3, and the degree of the other two vertices are 2. We see that vertex 1 is adjacent to 2, 3, and 4, which means there's a typo in this matrix. There should be -1s on the rest of the row and column, because 1 is adjacent to every vertex. Similarly, since 3 is adjacent to every vertex, we see -1s along the third row and on the third column. And the one remaining entry is 0 because 2 and 4 are not adjacent. So according to my theorem, it's going to involve what happens when I remove a column in a row. Because it turns out the determinant of the original matrix is 0. But if you remove any column in any row, you get a smaller matrix. And it turns out that the determinant of the matrix in this case is 8. And that ends up being the number of spanning trees of this graph. So the matrix tree theorem is that the number of spanning trees of a graph is given by taking the determinant of what's called the reduced Laplacian. So you've taken your Laplacian matrix and you've deleted some row and column. There are many accessible proofs of this theorem that can be found online, but they almost all use facts about the determinant that you might not have learned before. Like the proofs I'm used to either involve what's called the Cauchy-Binet formula or the Leibniz formula for the determinant, and both these are a bit more complicated. However, I want to show how we can get Cayley's theorem from this result. So in this case, G is the complete graph. Then the Laplacian matrix is the diagonal entries are n minus 1, and you have -1 everywhere else. For instance, if we look at K3, this is what we get. And a fact I'm going to use from linear algebra is that the determinant of a matrix is also equal to the product of its eigenvalues, including each eigenvalue, the number of times the eigenvalue appears in this product is the multiplicity of the eigenvalue. And so for this particular graph, we need to look at the eigenvalues. Turns out actually factoring this characteristic polynomial is a lot of work. But if you happen to know the answer in advance, you can actually calculate things. So first, just take E1 minus any other EI. Here, EI is the standard basis vector. That's 1 in the ith spot and 0 everywhere else. Let's see what happens when I multiply this vector by the Laplacian of the complete graph. Well, if I multiply the first row by vi, I'm going to get n minus 1 for the first entry, -1 times -1 for the ith entry in the sum, and then everything else is 0. Because these two terms correspond to 1 here and -1 here, and since everything else is a 0, it gets multiplied by 0. And so the first entry is just the number n. For the rest, you end up seeing that you get 1 times 1, -1, and -1 times 1, so you get 1 minus 1 for nearly everything else. So for most of the rest of the entries, they're 0. However, if you look at the ith component, then you're multiplying the ith row of the Laplacian times this difference of vectors. Well, since vi is adjacent to v1, there should be -1 times 1 here in the summation. And then once you look at the I plus first column, then you get a n minus 1 times -1. So when you add them all up together, you get -n. In particular, this looks like, if I factor out the common scalar of n here, e1 minus ei again. Oh, and for corrections, this should be I plus 1. So in particular, each of these vectors is an eigenvector with eigenvalue n. That's the point we just discovered. It's also pretty clear that these vectors are linearly independent. And there's a typo here. This should be n minus 2. So there's n minus 2 of them. On the other hand, if you add up all the standard basis vectors together and multiply them by this matrix, well then what happens is these all become -1s, n minus 1 times, and then 1 n minus 1. And so all the entries become 0. And so in particular, you see that the dimension of the eigenspace for eigenvalue n is at least n minus 2. On the other hand, the dimension of the eigenspace for 1 is 1. These technically should be inequalities. But then it happens to be that n minus 2 plus 1 is n minus 1, which is the dimension of the vector space we're working with, because we've deleted a row and column. And since these numbers add up correctly, that means this actually has to hold with equality. It couldn't possibly be bigger, because then you'd have more eigenvalues than you have dimension, and that's not possible. So in particular, this tells us that the eigenvalue n has multiplicity n minus 2. And the eigenvalue 1 has multiplicity 1. And so the determinant of our Laplacian is the product of the eigenvalues. It ends up being n times n minus 2 times 1, which was Cayley's theorem. Now this matrix tree theorem can be generalized in a way that's actually quite crazy. So suppose you take your graph and you put a variable for each edge, and then you create a generalized Laplacian as follows. For the diagonal entry 1, you add up the variable names on every edge incident to 1, so it's a plus b. Here you put every edge incident to 2, a plus c plus e. Everything incident to 3, so d and e, and so on. And then off the off diagonals, if I is adjacent to j, like 1 is adjacent to 2, you put negative and then the variable name for the corresponding edge, which in this case is a. And so you get this symmetric matrix. Now remove a given row and column. In this case, it looks like I removed the last row and last column, and compute the determinant of the resulting matrix. So I'm not going to go through all the calculations, but the point is certain terms end up canceling, and in the end you see that you get a positive sum. In particular, every single entry in the remaining summation has a coefficient of 1. It's a product of exactly 3 variables with no higher powers. And most importantly, if you color those edges in, like say ACD here, you see that what you get is a tree. In particular, each of these monomials corresponds to the edge set of a spanning tree. And so you see exactly every spanning tree appearing here. Note that if you set each of these variables equal to 1, then this gives you the number of spanning trees, and this gives you the original Laplacian, and so you recover the matrix tree theorem. Of course, in practice, the reason why we like the matrix tree theorem is because there's many different ways to compute a determinant, but once you're putting in variable names for the entries, the computation of the determinant actually gets too hard, and so at this point, this theorem is, well, it's harder than just trying to find an algorithm to list the trees.